different type of images, overall clinical utility. Then we will go to detailed case studies. So we have three workstations, 3 laptops actually, all of them are workstations. We will have hands-on each one. I will project the case, you can have hands-on the workstation. That's what we have planned today as the agenda. 2 to 4 centimeters and not more than that. About 5 years back, we bought 8 centimeter and then 16 centimeter wider detector. Width in the sense in the Z axis. So the coverage what it can give in this axis is now become 16 centimeter. Here we have 8 centimeter system. The advantage with this wide detector is that one, it needs less scan time. When scan time is less, invariably motion artifacts will be less. And that enable you to do better cardiac studies. The detector makes the essential difference here in wide detector CT. All the wide detector CT what GE has gemstone detector. The gemstone detector is faster or the fastest detector in the world, which has no afterglow. Afterglow is like when any X-ray falls on the detector surface, it will remain in the detector surface for some time. And this time, during that time, you cannot use the detector for detecting another X-ray event, or it's called dead time. Whereas in gemstone detector, there is no dead time, so that you can immediately use another view or another energy. This actually opened up something called dual energy. We will get into those details. As the detector is very fast, you can collect almost 4 times of scan data in one rotation compared to a normal CT. So this has opened up a new thing called high definition imaging. CT is for projection, back projection, image. Very simple. That's the principle of CT. Projection. You put X-ray, pass through the patient, falls on the detector, that creates projection. More the number of projections you take, more will be your resolution. So we go up to a resolution of 230 microns with revolution CT what we have here. So that's an overall nutshell introduction what has happened, and of course we are more concerned about those. There are good iterative reconstruction available by default in the machine called SRV, which reduces the dose somewhere starting from 50% to 80% or 89% in some cases, and which opened up something called ultra low dose lung screening, all those things. Now we will see why we needed dual energy. Okay. As I said earlier, X-ray tube, patient, detector. When the X-ray passes through the patient, what it will undergo? It will undergo attenuation. This attenuation is actually summed up. You are having bone here, soft tissue, air, right? Fat. So when it passes through all this tissue, what you get on the detector is a sum of the whole attenuation, and that is what is called mu, or linear attenuation coefficient on that part. This mu value is the difference between mu value of two tissues are very, very minimal. For example, water and soft tissue, the mu value is very, very minimal. It's 0.1% difference. But we are seeing water as black and soft tissue as white or grey on a CT image. Why it is happening? That's because of this CT equation. This equation was by Sir Godfrey Hounsfield. He just puts very simple this equation down. I know all of you know this very well. So why this equation was put is to amplify the small difference in attenuation as big, so that your eyes can differentiate. And he has related that with water, so that it's uniform. Your Siemens machine or GE machine or Philips machine, if you are not relating that to water, each machine will give their own type of images, right? So you want to make uniformity across all the CT machines. You need a standard value. That standard was with water. That's the reason why if you are seen when you are installing machine, engineers do something called water calibration. Okay. So Sir Godfrey Hounsfield has given us. So when we take the projection, we back project to form the image, and attenuation values are converted to Hounsfield unit by this equation. Okay. Now, a simple question. When you are measuring Hounsfield unit, how you measure Hounsfield unit? You put an arrow. When you are measuring the Hounsfield unit, operating potential, correct? You need kV and ME for exposure. If you are using 100 kV, all the X-ray photons are not at 100 kV. It starts from 0 kV to 100 kV. It's a range of X-ray beam, and that is called X-ray spectrum. So this is your X-ray spectrum. Simple question. At high kV, the attenuation will be low or high? At high kV, whether the attenuation will be low or the attenuation will be high? Attenuation will be less at a higher kV, correct? For any tissue, because it will pass through. Now you are having a range of X-ray here, starting from say 0 to 100 keV, all the energies are there. So each same material will see different energy beams as it passes, because your beam what you are using is called polychromatic beam. What is it? Polychromatic beam, which contains all the energies. When there are a lot of energies are there, the attenuation what we are measuring is actually not the default attenuation at that energy. It is actually the sum of all the energies. Measuring as Hounsfield unit is actually not really the actual Hounsfield unit. Rather, it is sum or the average of all the energies. It's not true Hounsfield unit. How that is going to be a problem, we will see in the next slide. Hope this is clear now. Okay. So, problem here is we are using polychromatic beam, and the attenuation what we are measuring is not actually true attenuation or not true Hounsfield unit. But we had been doing this for ages now. So almost 50 years we have been using it. We are tuned to this, we are okay with this. But that okay is not very good. I'll tell you reasons. Now, can you see a cyst here, renal cyst? What should be the Hounsfield unit of renal cyst? What? The moment I give contrast, did cyst enhance any time? It don't. Simple cyst doesn't enhance. But when you measure Hounsfield unit, after giving contrast, it has gone up by 10 units or 10 Hounsfield units. Why? We know that it will not enhance. Then why the Hounsfield unit went up? The reason is, you see, kidney enhanced with contrast, right? Kidney is enhanced with the contrast, and the kidney work like a high density filter within the body. High density filter. So what it will do is, it will increase the energy, mean energy of the X-ray beam within the body. So your attenuation value will change, and that's the reason why cyst shows a pseudo enhancement. This has been well documented. So what was the reason? Since you are using a high power X-ray will go inside the cyst. When it goes inside the cyst, by default your Hounsfield unit will go up. The reason is your econ algorithm is unable to understand what energy came. Pseudo enhancement of cyst has happened. This is because of what problem? The polychromatic beam. You have seen what you measure as Hounsfield is enhancing. Why the cyst is enhancing? This is because again issue with the polychromatic. Now, it has a tissue inside. It has something inside. There is actually a cholesterol calculus, which we are not able to see on a normal CT image. Why we were not able to see that on a normal CT image? Because the attenuation of cholesterol cyst within the bile are similar. So CT machine was not able to surrounding wire. So actually there is some object there, but we have missed it totally. The moment you go for something called monochromatic or material image, you will be able to see. This is the reason why we have now moved from a normal CT to a spectral image. You see in the spectral image, you are able to see the cholesterol calculus. Why? Because we are going for material based image. So measuring true Hounsfield unit and going to material will help you to be specific on lesion, specific on object which you are looking at. That's the basic reason why we have introduced dual energy CT. The inadequacy of normal CT is that it was not able to differentiate attenuations very well. So, for example, when you have done an angio, you may see calcium and the blood vessel both are having same density. Many times you see calcium is getting into the blood vessel and unable to measure the proper stenosis there. Why this is happening? We call it as calcium blooming. This is because of attenuations are overlapping. But if you can make iodine alone image, then what you will see? Only iodine. You will not see the calcium. So you will be able to measure it better. So this is the reason why we have introduced dual energy CT. So this is to overcome the inadequacy of a normal CT. Dual energy CT was made. Now, getting little bit more deep into the physics of this, please stop me if you are not able to follow at any point of time. I will repeat. How we do a dual energy acquisition. Okay, very simple. You know this equation always, the old famous equation, I is equal to I0 e raised to minus mu.
If monochromatic is truly monochromatic, or is it like same as is monochromatic and fully monochromatic, or
from two attenuation values?
Okay, it's calculated by
it is calculated. It is calculated from two references. We'll see that. So we have one material here. Okay, one material. We don't know. Maybe water. Let's take. Okay. We are putting one energy beam. So we are putting 80 kV beam. So the original intensity. This is E1. Let's take E1 as 80 kV. Okay. So I put I0 original value intensity. Say X in some intensity of X I have put. Then the material is here. This material is water. It will undergo what? Attenuation. Correct. So what you will get is the measured value. This is your original X-ray and this is material which will undergo attenuation, and this is your measured intensity. So instead you can measure this, then easily you can say attenuation of this material, that is mu, at energy 1 we can calculate. It's very easy. The attenuation is subdivided into two things: mass attenuation, and this is mass attenuation and this is density attenuation. Actually, when we studied, we only studied mu, right? Actually, the mu has two components. One is because of density, second is because of mass attenuation. That's a total attenuation. Okay, so I just divided that into two. Actually, mu at energy, it's very easy. Put a known X-ray beam, you measure the X-ray beam after attenuation, and you can calculate what is attenuation. Very simple. And each material will follow an attenuation curve at each energy. For example, water. At 40 kV to 140 kV, water will follow. Each kV there will be some attenuation. That attenuation is represented as a attenuation curve. Okay? Very simple. So far so good. Now if you know, for example, I don't know the material, but I have measured the attenuation at 80 coming to this point, then I can happily say, yeah, what you are encountering is calcium. It's very easy. If you know the attenuation value, attenuation will not change. One material's attenuation will be same at that kV at anywhere. Whether you do it here or do it in another hospital, that is the same. If you know the attenuation value, then you can say what material it is. Correct? Right. Using this graph is like our fingerprints. It will not change for any material. It will be affected because when you are at when there is an osteoporosis, the material is changed. It is not normal bone.
Calcium is there.
Calcium is there. Along with that, you are having
Other material.
other material also. That is exactly what the attenuation curve will show. It will say the attenuation is reduced. Right? Now this is okay. Fine, great. One material, one energy, we can easily measure and say this is this material. But in real life, the scenario is different. Water and iodine. Now if I measure the attenuation using a single energy, and I am going to ask this question, can you say how much is attenuation from water, how much is attenuation from iodine? Can you measure? You cannot. Because what you are going to get here is a sum of the attenuation. This is what exactly the problem with current day CTs. What you measure is the sum of the attenuation. This is what I explained in the first slide. So when you are measuring the sum of attenuation, it's now look at the equation. Earlier this equation mu was by one material, correct? Now that it has come with another material, and if I ask you how much is this and how much is this, you cannot differentiate because it's sum of the attenuation now. That's why plus sign is there. Attenuation by material A and attenuation by material B, or water plus iodine will be your total attenuation now. Now we are blind. We don't know how much is from this, how much is from that. The solution for identifying these two is simple. You expose the same material with another energy. Okay. Now look at the equation. This is your equation at energy 1. This is 80 kV. Okay. So you got a sum of attenuation by material A and sum of attenuation by material B at 80 kV. Now then you have exposed that with 140 kV. When you have exposed that with 140 kV, you again got another attenuation at energy 2, that is 140 kV, mu A, mu B, rho B at energy 2. Now there is a question. Does the material change? Material is not changing. What we are changing there? Energy. The material will remain the same, but you are having two energies. Now, which are all the known? This one you can measure, correct? This one you can measure, correct? Two knowns. Which are all unknown? This is unknown and this is unknown, correct? So, if mathematics says if there are two knowns and there are two unknowns, you can solve the equation, which you have learned in our 8th standard or 7th standard. In simple algebra, we have learned if there are two knowns or two unknowns are there, you divide it, subtract, whatever method you use, you will be able to get this right. This is the reason why we are doing exposure with the two energies, 80 kV and 140. It's clear? Okay, so simple. Two solutions and two unknowns. We can make simultaneous equation, then identify the two material. Okay, so what we need? We need to expose the same material or the same anatomy with the two energies. Once you do that, then you can measure the mass attenuation coefficient of material A, which is iodine, or material B, which is water, clearly from these two equations. Okay. This equation you have seen in the previous slide, correct? So, 80 kV attenuation. Now I have changed that A and B as iodine and water. Okay. You see, rho I, mu I, rho W, mu W. Okay. I put it as iodine and water instead of A and B. The previous slide it was A and B, right? This is A and this is B, correct? So I changed that A and B to iodine and water at two energies. Okay. The same material, same block, same experimental object, iodine, water. We exposed it to energies and we got two equations. The attenuation by water is how much inside this? How much is attenuation by water in this material? I know the attenuation of iodine. Iodine has a standard attenuation value at a particular energy. If the standard table is written somewhere, you want attenuation, total attenuation minus attenuation of iodine. Minus attenuation of iodine. You know the iodine value. So you make the iodine value, known value 0, then what you will get? You get the water image. So you take this sum of equation you got, total attenuation you got, and make known materials. What is that? Known materials. For example, iodine's attenuation, if you are putting 0, then you will get water image. On the reverse, if you put water value as 0, what you will get? You will get iodine image. This is why whenever you are going for a dual energy analysis, you say material pairs. You might have noted, we don't call it as material, we call it material pairs. Iodine, and then you will see something in the bracket. The bracket is the known material which is suppressed. Okay? We will see that when you do the hands-on, we will see how the materials are suppressed. So, for this what you need to know the attenuation curve, and you have to feed that value into the workstation. This is already there, GE has done. You can also create your material and put it. So we have put almost all the default fat, water, iodine, all this default value we have put inside the attenuation curve. That is from 0 to 1 MeV. All the energies we have loaded inside. So you know the attenuation value of a material, and from the group of two materials, if you put one material's attenuation value as 0, you will get the other material. For example, iodine value you put 0, you get the water image. If you are putting water value 0, then you will get iodine image. And this is why it is called material pair imaging.
Can we add lipidol?
Lipidol, yes. Lipidol is iodine. Partly iodine. The other component is a fat component, which is very low attenuation.
So we can't differentiate between lipidol from iodine. We can't differentiate lipidol from iodine.
We cannot. We will see as a single. The moment you want to suppress lipidol, you can suppress iodine.
But we need to suppress, no? We need to differentiate.
You cannot.
Actually, we have done some cases also, GSI images, in that iodine is pressed on the vessels, but
we were not able to differentiate between iodine in the vessel, but from lipidol in the vessel.
So we practically problem.
That was the problem.
Both are in iodine.
Both are iodine attenuation. If you suppress iodine, both will get suppressed.
But we had fat also in lipidol, so can this be
It's mixture. It's very small quantity mixture. It's very difficult to differentiate. Because one box will contain both iodine and lipidol together. So it will be a sum of the attenuation, and iodine is more prominent. Compared to fat, attenuation is very low. So the attenuation contribution is more from the iodine part.
Iodine part of the lipidol.
So it will work similar to iodine material. I have this case of taste follow. Now, 2-3 important postulates. Okay, just remember, it's very simple. The first one I have already told you. The attenuation of a material will be higher at a lower kV. For example, you are having, when you are, see, how you know, when you are taking plain X-ray KUB, what kV you will use? Low kV, right? Why you are using low kV? To get more fat attenuation you want to. So we are having soft tissue differentiation requirement. What you do is you reduce the kV. That means the material will show more attenuation at the lower kV. That is postulate 1. The second one, higher attenuation material show high attenuation at lower kV. A high atomic number material, for example iodine or gold. These are all high atomic number material. They will show higher attenuation at a lower kV. Of course, this is actually an extension of this one, but on a high atomic number material. That's why if you look at, iodine is having a very high attenuation value at low. Attenuation of a material will follow an exponential curve. You can see the iodine curve, you can see the water curve. Okay. If you know the attenuation at say 80 kVp, and if you know the attenuation at 140 kVp between two materials, iodine and water, then actually you can extrapolate all attenuation of these two materials along the entire energy range from 40 to 140 keV. For example, I have measured the attenuation at this point. I measured the attenuation at this point, the given sample, patient's body. We measured these two. Then you can extrapolate at any energy levels. For example, 90 kV, you want to see how water behaves and how iodine behaves. Okay. Now, if you are reducing the kV to say 50, now by differentiation between the water and iodine becomes much better, correct? Because iodine will be shown much better because iodine's attenuation is very high. This is what we do by doing monochromatic imaging. What is that? Monochromatic imaging, where we play with the energy of the beam. Actually, we are not changing anything on the scanner. We are taking 80 and 140 data. On the 80 and 140 data, you know the attenuation curve, you change the default values of attenuation. Okay, this is okay? This postulates are fine? Yes, sir.
Here the X-ray is monochromatic or polychromatic for 80 and 140?
80 and 140 are polychromatic beams. What we measure is the peak attenuation values. The spectral acquisition, one is material based, which you have seen how it is coming, right? You suppress the attenuation of one material, you get the images of the other material. Now there will be a question, suppose there are three materials are there. How I will get that? It is very difficult. We can do, since you are using only two energies for acquisition, you can differentiate only two materials. Okay. For example, when you are doing an iodine image of say iota, your water is suppressed. Iodine, water is suppressed, and you get the iodine image of the iota. In that, definitely you will see bone. There will be a natural question. I have suppressed, which is soft tissue or water. So suppose there is a method to have three acquisitions or three energies and then add iodine, water suppressed, bone suppressed, then you will be able to do that. That's called triplets.
But you told that in your machine you have feeded all the values for bone.
At a given point of time, you can
suppress
only two materials.
So if we suppress bone and iodine, we consider for iota. Water now? Because we are
can just make a like calcium image, for example, or just a water image for that matter. So will it help? Will it help us?
See, if you want to suppress the bone,
Right.
then we'll say iodine bone, iodine calcium,
Exactly.
iodine HAP. We do that when you are looking at calcified plaques inside the blood vessel. We can do iodine HAP. But in that image, soft tissue will be there.
For soft plaques and calcified plaques, we have to do two separate subtractions. One time for soft tissue and one time for calcium.
Right. So, see, you need not have to do any reconstruction there. You just need to change the material. When you are reviewing it, see, ideally, whenever you are reviewing, please don't go by a single material pair. Do the reverse also always, and then look at how it is behaving. Is okay? So what type of image you get first is called material based image. The second type of image what you get is called monochromatic image, which is like attenuation at 40 to 140 kV, 101 energy levels you can get. And of course, once you have done this acquisition, you can put an ROI and measure the atomic number of that material. For example, the atomic number of a renal stone, 6.9 is uric acid, 13 plus is calcium oxalate. So if you put an ROI and you can measure the atomic number of a material. So it's very specific. So three type of images which are seen: material based, monochromatic, of course atomic number images or Z images.
So this is based on the attenuation of band of particular material, the third one, atomic number.
Because you are exposing that material into energies. Now you know which material, you know the attenuation curve, then you measure the ROI, put an ROI, it will say what is the attenuation. Any doubt?
No, whenever we did some cases on GSI, our HU on NCCT acquired initially, vis-a-vis comparison of virtual non-contrast is always different. And probably is because polychromatic attenuation would produce a different HU.
Value and monochromatic.
So that means virtual NCCT would have a better and truer.
No, what we have to do is near approximate value. The near approximate value of attenuation will be for an 120 kV plain image. You want to do a material suppressed iodine image, then 80 keV should be your keV selection. At 80 keV, it will give you similar attenuation of that of 120 keV polychromatic.
But that leads to another question. For example, this graph wherein you are showing a photon, like a photon of 140 as well as 40 keV on this diagram. So why is this need of 140 keV? Why? Because we know that from our physics that the attenuation is higher on the lower side of the spectrum.
Correct. Now you are having a case where you wanted to see bones.
Yeah, but that will be calcium.
Bone.
Right.
You want to see bone better and soft tissue suppressed. Then you have to go for a higher energy. For example, you are reviewing abdomen. Soft tissue abdomen, you would look at 60, 70 keV. It will be very good. You want to see there is a bony erosion, you please change your keV to 100 or 120 or even 140.
So how is it different from the windowing that we already have in our older CTs?
Okay, window width and window level purely plays on the Hounsfield values. It is not playing on the attenuation values. It's not playing on the energy or monochromatic attenuation values. Whereas your monochromatic imaging plays actually on the different energies, what will be the attenuation. So that's why we say material based and monochromatic images are more accurate than the normal polychromatic images. So how to review, for example, the same case, you want to see the soft tissue abdomen, review at 60 to 70 keV. You see good enhancement of lesion, everything you are seeing in the soft tissue, liver. Now you want to see the bony erosion or a bony beds. Increase the keV to 140 and review. Same setting like window, how you adjust, just scroll it left and right. Okay.
Whenever we do the case with virtual non-contrast, that would be better rather than taking a NCCT.
We can do that.
Which will
We
be
did a
good,
case.
which will be better?
Whether to go for an NCCT
Which
or...
would be better? That is our question.
Okay. To see, there are few things are there. We want to see the lesion and identify the lesion better. Then monochromatic images at low energy is good. If you want to quantify, then you have to go for iodine images and put an ROI. That is more accurate than your HU values.
No,
Just on that image.
No, the
We want to
question
see
is,
how much the contrast has increased, how much the attenuation has increased. What is the
Baseline
HU and
You
NCCT?
want to measure on HUs only?
Yeah, age more than 20 or more than 10. What else we have to see for NCCT, virtual or the actual NCCT?
You can measure on virtual NCCT the normal value at 80 keV.
Okay.
Yes. Then compare that with your monochromatic images or monochromatic at 60, 70, 80, whatever. See, by default, soft tissue is around 68 keV is the best CNR, contrast noise ratio for soft tissues.
If I change the energy, then the attenuation HU value will change?
Of course it will change.
It will change. So, if I am measuring NCCT on 80, then I have to measure contrast on 80 only, or I have to change?
That is where you get the peak attenuation. There is something called peak attenuation by that material, and we call that as optimal CNR, optimal contrast noise ratio. Optimal contrast noise ratio will have a peak. That peak is by default most of the time it's around 65 to 68 keV for soft tissue enhancement. For example, liver lesion, HCCs. So you should measure that value. I will show you how to do that also.
If I am having a liver lesion and I have done contrast imaging in GSI, now I want to measure how much it has enhanced. So I'll see NCCT on 80 keV and enhancement on 60 keV.
So this 80 keV will be a monochromatic one or polychromatic?
Monochromatic. 80 keV is monochromatic always. When the moment you say keV, it becomes.
So these all will be a derived images from the initial
Yes.
acquisition.
And measure the ROI for the plain image. And for the contrast, make it 68 keV and measure the peak enhancement. We always go for the best enhancement.
There is no standardization or any particular criteria that
Because this is by
changing the KV.
Changing KV will drastically change your enhancement values.
Yeah.
That is where we go for this particular value called optimal CNR, optimal contrast noise ratio. By default, we have through experiments, whatever we have done, we know that 65 to 68 keV, you can actually visually see that.
There are no known criteria for that. Whatever.
This is the many articles. Even Dr. Dushan Sahani was the first person who has clearly commented on abdominal lesions are seen well at 68 keV. So there is a publication also we have done in Asia.
So it depends on institute how they are seeing the things.
More or less it will be defaulted to that value. For us also, I have seen when you are changing the KEV from 40, it will be very good. The enhancement will be very high. But if the noise will be too high.
Quantification, the thing is about quantification.
Quantification, you default to one value for all patients.
All patients we have to.
And I think 70 keV, I think we have said that. 70 keV. 70 keV. So we have put 70 keV as standard in the system. So if machine is giving monochromatic automatic, it will come at 70 keV. So there have been different technologies were used by different vendors, evolved during different times to do the dual energy acquisition. First one was fired together. Basically the acquisition is done by not a gemstone detector, normal detector. So you needed two X-ray tubes and two detectors because the detector was not very fast. So once you have done this acquisition with this, then you cannot actually make energy beams or something out of this because these are two different acquisitions. What Siemens do, this is done by Siemens, what they do is they use image-based methodology to get the virtual non-contrast or polychromatic or material. That's image-based, not raw data-based. But we do raw data-based. That's where you can actually put an ROI and quantify the concentration of material. Anyway, we'll come to that. The other one is helical, rotate kind of mechanism. This is a very premature thing. Okay. So we can use it only for some gout or some stone identification. Then in between something came called twin beam. They split the beam at the X-ray tube level with a gold filter and a tin filter. But again, acquisition is not simultaneous. So you have to minimum you have to do a 180 degree opposite rotation. Then only the same material or same anatomy can come under same two different beams. Again, the differentiation of materials were not very high. It was only 6 keV difference at 50% photon gain, and it need to be slow pitch. Then of course dual layer CT. This is used by Philips. They have 2-layer detector, the yttrium layer and a gadolinium layer, 2 detectors. And according to their theory, the yttrium layer will absorb all the soft X-rays, means the low energy X-rays, and the high energy will go to the gadolinium layer of detector. In theory it is good, in practical scenario is different because attenuation curves overlap. Again, differentiation is slightly a problem, but they go by that technology. G goes with fast KV switching, ultra fast KV switching, where we expose 80 and 140 alternate. You know the switching time between two energies? 0.25 millisecond. It's so fast. Of course, the disadvantage, I will not say disadvantage, it has an advantage. At the same time, the disadvantage I can say, you have
radiation dose high in this single source Hosp case than dual layer.
That's a very interesting thing. This is because you are going to expose in one single energy and you are not using two beams. Okay. Very interestingly, here also you take 360-degree rotation, you expose it for 1 second. For example, at a particular MA, here also you are going to do same 1 second, same 360-degree rotation. So dose is not going to increase because you are alternating between the energies. And this is called dose neutral technology. Here also it's a single dose neutral technology, but when you are using two layer of detector, one layer of detector will have a higher intensity value and the lower detector will have a low intensity value. To compensate that difference, you have to use a higher MA in sandwich detectors, which is a known fact.
And how do you scan?
Here we do this technology.
In the other one?
Yeah.
Single source?
You rotate and rotate. This is called rotate, rotate. Dual source, rotate, rotate, split beam, dual layer and fast KV switch.
Here we are using this gemstone and they are rotating.
There it is gadolinium based detector. You have to do rotate, rotate. So, of course, advantages and disadvantages I have written it here. This is from some publication. Okay. So, dual source CT, since it is using two X-ray beams, the average dose is almost like 1.5 to 1.7 times compared to a normal other methods. I will not say normal, other methods. Okay. Single source helical, this method is not very popular because it cannot, it's again image based, it cannot differentiate material, you cannot suppress one material and get one material because it works only on the image. When the moment you acquired an image, you cannot go back to the material. Image is image, is in front of you. You cannot go back to the attenuation values. If you want to go back to the attenuation value, then you should have the attenuation data with it. It's actually loading the raw data inside. Okay. Then dual layer CT, you have seen dose is high observation at the lower layer. Okay. And other challenge is that gadolinium the peak to acquisition is more than 40 keV. 80 and 140, more than 40 keV. So best differentiation between two materials can be found either using fast KV switching or a dual source CT. Both of them will show good difference between, because dual source you are using 70 or 80 kV, the other X-ray tube is using 140 or 130 kV. So you are having good difference in their attenuation. See, whenever your attenuations are measured at extremes, your differentiation of material will be better. That's what you might have looked at this curve. See, when you are exposing at this point and when you are exposing at this point, the difference is high. So your curve will be more accurate. Whereas if you are narrow down the curve, it's very difficult to extrapolate this side or extrapolate that side. Understood? Of course, pluses and minuses, when you are having any moving organ, okay, for example, heart or blood vessels which are pulsating, if you are using a split beam or a dual source, you may not be able to capture them in the single anatomical position, same anatomical position, one after the other. That's because the acquisition time between two energies are nearly 75 milliseconds apart. So within that, what will happen? The anatomy will move. So this is a known issue with that. Whereas if you go to rotate, madam, as you asked the other machine the time is almost like 1 second or 2 seconds. So that's why you cannot use it for any body application. Only you can use for stone and gout, which is a non-moving out. Whereas when you go to fast KV switching or a dual layer, you are almost nearly 0 millisecond difference or 0.25 millisecond difference. Your anatomy is same, it's not changed much. So you will be able to measure the attenuation of that moving anatomy better using either dual layer or the fast KV switching. So how we do the fast KV switching? So you can see the animation. So green and the blue. Green is high KV, blue is the low KV. If I show it very slow, this is how the attenuation happens. Can you see this curve? Can you see the graph? When 80 is there, 140 is not there. When 140 is there, 80 is not there. That means your dose will be neutral. That's why it's called dose neutral dual energy. Okay. Then there will be a natural question. What happens if, since you are changing the KV, you need to change the MA, right? Otherwise intensity will be different. Yes. That's why when the moment you go to any GSI acquisition, the MA, it's fixed by the protocol. It's fixed by the protocol, and internally the machine will modulate depending on the pitch, depending on your slice thickness, and depending upon the field of view, the system will automatically change. It's a GSI with this much default value of CTDI. That's our protocol is. Internally, inside the system, it will switch the MA. At a lower KV, the MA used will be lower. At a higher KV, the MA used will be, sorry, other way. At a lower KV, MA will be higher, and at a higher KV, MA will be lower. So it modulates MA during the acquisition and during the rotation. Okay. Now, once you have done this acquisition, okay, let's see that the data goes 80, 140 raw data goes, and these two datas are actually two separate data, 80 kV data and 140 kV data. We are using projection based, that is raw data based, and then you can create what all the type of image you get. 140 kV image, 140 kV image, 80 kV image. By default you will get material image, water or iodine, whichever material you want. Then you get into monochromatic images. That's why you might have seen whenever you do a GSI acquisition, the first set of data you get will be called QC, quality check image or quality control images. These are actually 140 kV images, not KV, sorry, kV images. Then you can create any material, say iodine image water suppressed or water image iodine suppressed. Then you can go for the third one, which is monochromatic. All this can be by default come to the workstation. You need not have to sit and create it on your workstation. So material based image, monochromatic image, QC image can be auto generated in the scanner. I don't know if the protocol is set, yeah. So it automatically, you need not have to do everything. Yeah, I want to see whether the iodine enhancement, I want to go to iodine image, no need. You can set your monochromatic at say 70, you can always ask for if it's a liver case, iodine image, water suppressed, monochromatic image, 140 kV QC image. Automatically this can come. You need not have to open in the GSI viewer format. You can, as you are seeing simply on your viewer, you can see the images. Directly, you can get it from the machine. The workflow is, earlier the workflow was little cumbersome. We have to create those images sitting in the workstation. Now they have defaulted it so that you can just auto boot it once you are done. So this goes to this particular radiologist desktop. So that's the improvement in workflow. We'll see some of enhancing renal lesions. Okay. So what they were telling is whenever you are having a epiphytic renal lesion like this, and you go to the iodine image and measure the iodine value, brightly enhancing lesions like RCC typically will have iodine concentration of 2 milligram per cc or more. Okay. This is easy for you to quantify and differentiate compared to the normal renal cortex and the RCC.
So need not NCCT immediate, just see the concentration of iodine in that particular region.
It will be high. It's anything, what many publications say, anything above, for enhancing lesions, any value above 2 milligram of iodine need to be considered as a lesion. The other thing you are asking about monochromatic images. When you are changing your monochromatic images to a lower KEV, your sensitivity and specificity goes up. So, for example, metastatic lesions, of course, this is iodine concentration. You can see at the arterial phase, it's 2.